general trial and error is still a dominant approach in asymmetric homogeneous catalyst design. Basically, here is your reaction, and what you want to do is to maximize enantioselectivity and sometimes also a reactivity. In this setup, you basically need to synthesize various catalysts and evaluate their performance. The overall procedure is expensive, time-consuming, and involves a lot of labor. Can we expedite the catalyst design with computational chemistry methods? The purpose of this webinar is twofold. First, we will overview the modern computational methods behind the asymmetric catalyst design. Second, we will learn how to use the Schrödinger platform to do that. How to design an asymmetric catalyst with physics-based modeling. The first thing to do is to identify a reaction for a non-single catalyst. Next, in the second step, we have to identify stereoselectivity determining transition states. And finally, the third step is to calculate %TE based on free energy difference between these transition states. Basically, step 1 to 3 is the first objective that we were talking about a few slides ago. This is about understanding the mechanism of the generation of chirality specifically. A better way to calculate %EE is to take into account the ensemble of transition states. Indeed, most transition states adopt more than one law of energy conformation. Thus, it is important to perform conformational search on transition states. In the next step, we have to repeat the same procedure from step 2, but this time we do that for each new catalyst in our list. At the end of the day, or whenever the calculations are done, we have this nice column which represents catalyst identity, %TE relationship, and this is all we need for an asymmetric catalyst design. One important thing to note here is that everything we have been doing till this moment is only a necessary condition for an asymmetric catalyst design. Ideally, we also need to consider a reaction rate. So a sufficient condition for an asymmetric catalyst design is this double column on the right, which shows structure, %EE, and TOF, or rate constant relationship. In practice, it makes sense to first screen selectivity and only after reactivity. Let us now overview on how to screen reactivity. Specifically, the question becomes how to design a fast catalyst. Here, our metrics could be rate constant, or in general case, a turnover frequency. Let us stick to TOF as an example. How to design a high TOF catalyst with physics-based modeling. The first step is, of course, to identify a reaction for a single catalyst. Now, here, we don't need to do that because we already know our reaction from the previous step. What we need to have, and this is the second step, is a full knowledge on the entire reaction mechanism, i.e. catalytic cycle. By knowing the catalytic cycle, we can calculate the TOF in the third step by using the known formula. Once again, a better way to do the same is to include a conformational search on all stationary points of your catalytic path in this game. This will allow to obtain a Boltzmann average profile, so we could calculate the activation barrier of the entire catalytic cycle and consequently the TOF value more accurately. In the next step, as you are probably already guessing, we have to repeat the entire procedure, but this time for each new catalyst. At the end of the day, we have this double column, and from it we can identify the best catalyst or catalysts. So the computational asymmetric catalyst design goal, based on physics-based modeling, is achieved at this point. Machine learning is relatively a new thing to many people. With respect to homogeneous catalysis, all that you have to know is that there are two flavors of machine learning cheminformatics and machine learning potentials or machine learning force fields. In both cases, the idea is to bypass the numerically expensive procedure of solving a Schrödinger equation. What is ML cheminformatics? Imagine you have this reaction, which is iridium catalyzed, photocatalyzed fast and chemoselective dehalogenation of aryl bromides. And imagine you even have some understanding about how this reaction works. In other words, you have some sort of catalytic cycle. For ML cheminformatics, this knowledge on the reaction mechanism is actually not needed. What is needed is some structure and property relationship, for example, 3D catalyst structure and rate constant that was experimentally measured. You take this as input, and the computer develops a mathematical expression that relates the catalyst structure to its property in the form of ML model. Think about ML model as a file or series of files at the end of the procedure. Now that you have an ML model, what shall you do with it? Remember that the model was created from 1,152 distinct catalyst structures, but what if you want to evaluate those catalysts that are not present in the initial list? Let's imagine we come up with 1 million possible structures as an example. The available ML model will allow us to predict the property for any given structure from this 1 million set. And this is the whole idea of ML chem informatics. For best practices, ML chem informatics best works for a series of catalysts which do not deviate significantly from one from another. In summary from this section, the key difference between chem informatics ML and physics-based modeling for asymmetric catalyst design is that the former is completely agnostic to the reaction mechanism. The idea of the platform is to combine all cutting-edge methods and theories of physics-based and machine learning modeling, automate them through a user-friendly interface, provide all sorts of technical and scientific support, including training of completely non-experienced users. The two most important modules for asymmetric homogeneous catalyst design of the platform are auto-reaction workflow and AutoQS-AR modules. Let us start overviewing the auto-reaction workflow module. After a user provides the input structures, the first part of the algorithm is to perform the conformational search on them. Here you can restrict your conformers by providing an energy window or by specifying the number of desired conformers. All subsequent steps are about quantum mechanical optimization, refinement, and analysis. Everything is done for you in the background automatically. You only provide input and obtain output, which is optimized structures, information on energy, and/or properties. Let us see how this works in practice. Our first reaction of interest is organocatalyzed asymmetric hydrogenation. Here is our reaction, and what we want to do is to design a catalyst that maximizes the percent EE. There is a total of 100 transition state structures. The reason for that is there are 2 transition states per catalyst, and I selected 5 conformers per transition state. So in total, we have 100 transition state structures. Without a reaction workflow, I can run all these simulations in a single click. What I would like to comment is the total running time, which is about 8 days. Actually speaking, most of catalysts completed within 2 to 3 days. It's just 2 structures that took about 8 days. The whole procedure takes about 8 days, one more time, by using these cloud resources and by running the jobs in parallel. If I was doing the same in a non-automated way, the whole procedure would likely take months, maybe even a year. Likewise, the experiment will likely take even longer, so the power of automation is really impressive. Example 2 is relevant to transition metal catalysis. Here is our reaction of interest, and what we want to do is to maximize this percent EE. To re-emphasize, the power of automation is amazing. It takes around 3 days without a reaction workflow, whereas it would likely take 1 year to do everything with non-automated DFT approach, or do everything experimentally. The last example I want to show is relevant to the design of high-rate constant catalyst. Imagine this is my reaction of interest, which is isotactic polymerization of propylene. And what I want to do is to design the fastest catalyst for this reaction. With the auto-reaction workflow, I can do any sort of substitutions presented in this slide, and we are pretty much unlimited in number of structures, assuming we have a good computer resources available. For this type of problem, I would only need to provide 3 Cartesian coordinates, plus the information on how to enumerate the reference catalyst and/or swap some catalyst fragments. Technically, I will need to hit enter 3 times, and that's pretty much it. AutoQS-AR module provides full automation around machine learning and informatics catalyst design procedure. A user only provides information on the catalyst structure and associated property. The rest is done for you automatically, and at the end of the day, you have your ML model built. Important part of Schrödinger platform is educational courses and tutorials. So we have over 50 tutorials available to users. Our customers range from highly experienced users to experimental chemists who came with absolutely zero experience and background. If you don't have any experience in modeling, we offer you the possibility to become a high-quality specialist, basically from scratch, by going through the series of specially designed tutorials.